September 23, 1943. The morning fog clung to the Bavarian countryside as Oberingenieur Friedrich Wolff carefully lifted the brass instrument from its protective case. Around him, 6 of Germany's most accomplished aeronautical engineers leaned forward, their breath visible in the cold air of the underground facility near Munich. For 18 months, they had been told by the Reichsluftfahrtministerium that American bombing accuracy was the result of luck, overwhelming numbers, and primitive terror tactics against defenseless civilians. The propaganda ministry insisted that American bombers flew in massive formations to compensate for their inferior targeting equipment. German intelligence reports claimed that American bombardiers relied on crude visual sighting methods, no more sophisticated than the iron bomb sights used in the previous war. Yet, something was deeply wrong with this narrative. American bombs were falling with a precision that defied explanation. Factories, railway yards, and military installations were being struck with surgical accuracy from altitudes of 25,000 feet. The mathematical impossibility of such precision using primitive equipment had haunted German aviation engineers for months. Now, in their hands, lay the answer. The Norden XV bombsight, captured intact from a B-17 Flying Fortress shot down over Hamburg 3 days earlier. What Wolff and his team would discover in the next 72 hours would shatter every assumption about American industrial capability and reveal a technological gap so vast that Germany's defeat was already calculated in gyroscopes, mechanical computers, and manufacturing precision that the Reich could never hope to match. The systematic examination of American bombing technology would expose not just superior equipment, but an entirely different philosophy of warfare. One where mathematical precision, mechanical perfection, and industrial automation had replaced human guesswork with mechanical certainty. The capture had begun at 04:15 hours on September 20th. Obergefreiter Hans Müller of the 3rd Flak Regiment had been tracking a formation of B-17s returning from a daylight raid on aircraft factories in Regensburg. His 88mm gun had found its mark, sending one bomber spiraling earthward in flames. The aircraft had crashed in a field outside Hamburg, its crew scattered by parachute across the countryside. Müller's recovery team, following standing orders to secure any intact equipment, had searched the wreckage methodically. In the nose section, protected by a reinforced compartment, they discovered the bombardier's station completely intact. The Norden Bombsight, secured in its gyro-stabilized mount, had survived the impact. Along with it were technical manuals, spare parts, and calibration equipment. Müller immediately contacted higher command, knowing that this equipment represented the most closely guarded secret of American bombing operations. The bombsight arrived at Luftwaffe Technical Testing Station 4 on September 22nd, transported under maximum security protocols. The facility, hidden beneath what appeared to be an agricultural research station, housed Germany's most advanced aeronautical engineering laboratories. Oberingenieur Friedrich Wolff, former chief designer at Heinkel Aircraft, led the examination team. With him were specialists in optical instruments, mechanical computation, gyroscopic systems, and bomb ballistics. They began with external observation, treating the device with the reverence due to enemy equipment of unknown capabilities. The Norden Bombsight was a marvel of mechanical complexity, housed in a deceptively simple bronze case. Weighing 55 pounds, it combined a telescopic optical sight with an integrated mechanical computer capable of solving bombing equations in real time. The gyroscopic stabilization system maintained perfect level orientation regardless of aircraft movement. To German engineers accustomed to manual bomb sights requiring constant operator adjustment, this represented automation beyond their current capabilities. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Wolff began his examination with the optical components. The telescope provided 20-power magnification with crystal-clear resolution across the entire field of view. German bomb sights typically offered 8-power magnification with significant optical distortion at the edges. The American telescope used precision ground lenses with anti-reflective coatings that German optical companies had never mastered in production quantities. Hauptmann Otto Schneider, a specialist in precision mechanics, examined the gyroscopic stabilization system. He discovered 3 gyroscopes operating in perfect synchronization, each one balanced to tolerances measured in thousandths of an inch. The gyroscopes maintained stable platform orientation, regardless of aircraft pitch, roll, or yaw. This meant that bombing calculations remained accurate even during evasive maneuvers or turbulence that would render German bomb sites useless. The mechanical computer represented the most shocking discovery. Hidden beneath brass covers was a maze of gears, cams, and differential mechanisms that automatically solved the complex equations required for accurate high-altitude bombing. The bombardier simply input target speed, wind velocity, altitude, and airspeed. The mechanical computer calculated lead angles, drift corrections, and release timing without human calculation. Dr. Heinrich Ritter, a mathematics professor drafted into weapons development, spent hours tracing the mechanical computational pathways. He identified gear trains that performed multiplication, division, integration, and differential calculations, mechanically. The precision required to manufacture these components exceeded anything in German industry. Each gear was machined to tolerances that would require weeks of hand-fitting in German factories. Yet, these bomb sites were clearly mass-produced. Every component showed evidence of machine manufacturing, with no individual adjustments or technician modifications. The Americans had industrialized precision to a degree that Germany had never imagined possible. The testing procedures revealed even more disturbing facts about American manufacturing capabilities. The Norden Bombsight operated in coordination with the Sperry autopilot system installed in American bombers. During the bombing run, the bombardier could actually control the aircraft through the bombsight, making fine course corrections to ensure perfect target alignment. The mechanical computer provided steering commands to the autopilot, creating a fully automated bombing system that removed human error from the equation. German bombers required highly trained bombardiers to manually calculate wind drift, target motion, and release timing, while the pilot attempted to maintain straight and level flight through anti-aircraft fire. The American system allowed the bombardier to concentrate solely on target identification, while the mechanical systems handled all calculations and flight corrections automatically. Lieutenant Franz Weber, a former bomber pilot, tested the site's tracking capabilities using ground targets. The mechanical computer locked onto moving targets and provided continuous tracking solutions. A bombardier could acquire a target 20 miles away and maintain perfect tracking accuracy throughout the entire approach. German bomb sites lost accuracy beyond 5 miles and required constant manual readjustment. The Americans had transformed bombing from a skilled trade requiring years of training into a mechanical process that any intelligent operator could master in weeks. This represented not just technological superiority, but a fundamental revolution in military philosophy. Where German doctrine emphasized elite training and individual skill, American doctrine emphasized mechanical precision and standardized procedures. The economic implications became clear as the team calculated manufacturing requirements. Each Norden bombsight contained over 2,000 precision-machined components. The optical elements required specialized glass factories. The gyroscopes demanded precision-bearing manufacturing. The mechanical computer needed gear-cutting machinery accurate to millionths of an inch. Germany possessed perhaps 10 facilities capable of producing components to these specifications, and those facilities were already operating at maximum capacity, producing other precision equipment. The Americans were installing Norden bombsights in every heavy bomber, and they were building heavy bombers at a rate of 15 per day. This implied manufacturing capacity for precision components that exceeded Germany's entire optical and precision mechanical industry. Oberingenieur Wolff began drafting his preliminary report to Reichsmarschall Göring's technical staff. Each paragraph contradicted fundamental assumptions about American industrial capabilities. He wrote that the captured bombsight represented manufacturing precision and mechanical sophistication that Germany could not duplicate. More importantly, it demonstrated that American industry could produce such equipment in quantities that made precision bombing a standard capability rather than an exceptional achievement. The report's most devastating conclusion addressed the strategic implications. German air defenses were designed to counter large formations of bombers using inaccurate area bombing tactics. The Norden Bombsight enabled small formations of bombers to achieve the same destructive effect through precision targeting. This meant that increasing American bombing accuracy would make German air defenses progressively less effective. Furthermore, the mechanical automation of bombing calculations allowed American bomber crews to spend more time on navigation, target identification, and defensive tactics. German crews, burdened with manual calculation requirements, were more vulnerable to fighter attack and navigation errors. The technological advantage multiplied across every aspect of bomber operations. Over the following week, the team conducted comprehensive testing of every bombsight function. They mounted the device in a specially constructed test rig that simulated bomber flight conditions. Compressed air systems provided gyroscopic power. Optical targets simulated bombing approaches from various altitudes and angles. The results consistently demonstrated accuracy levels that German equipment could not match. From simulated altitudes of 25,000 feet, the Norden Bombsight achieved targeting accuracy within 50 feet of the designated target. German bomb sights at the same altitude showed accuracy dispersions of over 500 feet. The 10-to-1 accuracy advantage meant that American bombers could achieve the same destructive effect with 90% fewer bombs. This had profound implications for bomber survivability. American formations could complete missions more quickly with fewer aircraft, reducing exposure to anti-aircraft fire and fighter attack. The strategic bombing campaign could achieve its objectives with smaller formations, shorter missions, and lower loss rates. Germany faced an enemy that was becoming progressively more efficient while German capabilities remained static. Dr. Ritter calculated the mathematical implications of American bombing accuracy improvements. If current trends continued, American bombers would achieve near-perfect accuracy within 2 years. This would enable precision destruction of individual buildings, railway switches, and manufacturing equipment. Strategic bombing would evolve from area destruction to surgical strikes against specific industrial capabilities. The psychological impact on German technical personnel was profound. For decades, German engineering had represented the pinnacle of precision and sophistication. German optical instruments, precision machinery, and mechanical devices were considered the world's finest. The Norden Bombsight demonstrated that American industry had not only matched German precision, but had exceeded it while achieving mass production that Germany considered impossible. Hauptmann Schneider wrote in his personal notes that examining the bombsight felt like looking into the future. The level of automation, precision, and manufacturing sophistication suggested that America possessed industrial capabilities that fundamentally differed from anything in Europe. German industry excelled at producing small quantities of handcrafted precision equipment. American industry had learned to mass-produce precision equipment to tolerances that German craftsmen achieved only through individual adjustment. The captured bombsight represented more than technological advancement. It embodied a completely different approach to warfare and industrial organization. Where German doctrine emphasized elite equipment operated by highly trained specialists, American doctrine emphasized reliable equipment that ordinary operators could use effectively. The Norden bombsight was sophisticated enough to achieve unprecedented accuracy, yet simple enough for rapid crew training. This philosophy extended to maintenance and logistics. The bombsight was designed for field repair using standard tools and interchangeable components. German precision equipment typically required factory-level maintenance and individually fitted parts. American bombardiers could replace major bombsight components in forward airfields using standardized parts shipped from American factories. The strategic implications were becoming undeniable. American bombing accuracy would continue improving, while German defensive capabilities remained limited by industrial constraints. The captured equipment revealed that America possessed not just superior technology, but superior manufacturing philosophy. They had industrialized precision warfare, in ways that Germany could not counter with existing resources. As September ended, Oberingenieur Wolff completed his comprehensive technical assessment. The document, classified at the highest security levels, concluded that German air defenses faced an impossible task. American bombing technology would continue advancing faster than German countermeasures could be developed. The industrial capacity gap meant that America could afford to equip every bomber with precision targeting equipment, while Germany struggled to produce adequate numbers of conventional defensive systems. The report recommended immediate restructuring of German air defense priorities and industrial production schedules. However, by late 1943, Germany lacked the resources to implement such fundamental changes. The Norden Bombsight had revealed not just technological inferiority, but strategic inevitability. The precision bombing campaign would succeed because American industry could produce precision targeting systems faster than German industry could produce effective countermeasures. In the underground laboratories of Bavaria, German engineers had witnessed the future of warfare. They had examined the mechanical embodiment of American industrial supremacy and found it technically perfect, strategically devastating, and industrially impossible to counter. The brass instrument that Oberingenieur Wolff had carefully lifted from its case represented more than bombing technology. It represented the mathematical certainty of Germany's defeat, calculated in gyroscopes and gears, measured in thousandths of an inch, and produced by the thousands in American factories that Germany could never hope to match. The second week of October brought disturbing news from the front lines that gave new urgency to the bombsight analysis. American daylight bombing raids were achieving unprecedented accuracy against specific industrial targets. The ball-bearing factories at Schweinfurt had been struck with surgical precision, hitting individual production buildings while leaving administrative offices untouched. Railway marshalling yards were being destroyed with bombs placed directly on switching mechanisms, paralyzing entire transportation networks with minimal ordnance expenditure. Intelligence reports from Luftwaffe pilots described American bomber formations that seemed to ignore anti-aircraft fire, maintaining perfect formation discipline during bombing runs that lasted 15 to 20 minutes. German bomber doctrine called for rapid bomb release and immediate evasive action to minimize exposure to defensive fire. The Americans appeared willing to accept defensive fire for extended periods to ensure targeting accuracy. This tactical difference reflected the confidence that precision equipment provided. German bombardiers, knowing their equipment's limitations, minimized exposure time and accepted reduced accuracy. American bombardiers, trusting their mechanical systems, prioritized accuracy over personal safety. The psychological advantage of superior equipment extended beyond technical capabilities to operational doctrine and crew morale. Dr. Heinrich Ritter spent October analyzing the mathematical principles embedded in the Norden Bombsight's mechanical computer. He discovered that the device solved differential equations in real time using gear trains and cam mechanisms. The mathematical complexity rivaled university-level calculus courses, yet the bombardier simply turned dials and read solutions from mechanical displays. The Americans had mechanized advanced mathematics, transforming complex calculations into simple operator procedures. This represented a fundamental shift in how technical knowledge was applied in warfare. German doctrine required highly educated specialists who understood the mathematical principles behind their equipment. American doctrine eliminated the need for mathematical understanding by embedding calculations directly into mechanical systems. Ritter calculated that training a German bombardier to achieve equivalent accuracy required 18 months of mathematics education, followed by 12 months of practical training. American bombardiers achieved superior accuracy, with 6 weeks of equipment familiarization and basic operational procedures. The time advantage multiplied across the entire training system, allowing America to produce qualified bombardiers at rates that Germany could never match. The mechanical computer's most sophisticated feature was its ability to compensate for multiple variables simultaneously. Wind velocity changes, altitude variations, target motion, and aircraft speed fluctuations were continuously processed and integrated into bombing solutions. The system updated calculations 50 times per second, maintaining accuracy through conditions that would overwhelm human computation capabilities. German bombardiers manually estimated these variables and applied corrections based on experience and intuition. The accuracy depended entirely on individual skill and judgment under combat stress. American bombardiers simply monitored mechanical displays that provided continuous solution updates regardless of combat conditions or operator experience levels. Hauptmann Otto Schneider discovered that the bombsight's gyroscopic system used electric heating elements to maintain optimal operating temperature. The temperature control system prevented gyroscopic drift that plagued German equipment during high-altitude operations. This seemingly minor feature represented sophisticated environmental engineering that German manufacturers had never considered necessary. The heating system required electrical power generation and distribution systems throughout the bomber. American B-17s carried generators, voltage regulators, and electrical distribution panels that supplied power to dozens of electrically operated systems. German bombers relied primarily on mechanical and pneumatic systems, lacking the electrical infrastructure to support automated equipment. This revealed another fundamental difference in design philosophy. German aircraft emphasized mechanical simplicity and reduced electrical complexity to improve reliability and reduce manufacturing costs. American aircraft embraced electrical automation, accepting increased complexity in exchange for enhanced capability and reduced crew workload. The electrical systems analysis revealed manufacturing sophistication that stunned the German engineers. Electrical generators produced precisely regulated voltage under varying engine speeds. Voltage regulators maintained stable power supply despite load fluctuations. Electrical cables were insulated with materials that maintained flexibility at temperatures of -60 degrees Fahrenheit. German electrical systems typically failed at high altitude due to insulation breakdown and voltage irregularities. American systems operated reliably at altitudes and temperatures that exceeded German equipment limitations. The electrical infrastructure represented an entirely separate technological advantage that multiplied the effectiveness of precision bombing equipment. By mid-October, the team had documented over 300 separate technical innovations in the captured bomb site and its supporting systems. Each innovation represented solutions to problems that German engineers had either ignored or considered unsolvable. The cumulative effect was equipment that operated reliably under conditions that would disable German alternatives. Oberingenieur Wolff realized that the technological gap extended beyond individual components to systematic engineering approaches. American designers anticipated operating conditions, failure modes, and maintenance requirements during the design phase. German designers typically addressed problems through operator training and maintenance procedures rather than equipment modification. The Norden Bombsight included features that prevented common operator errors, compensated for equipment drift, and provided diagnostic information for maintenance personnel. German equipment required highly trained operators who understood equipment limitations and applied corrections based on experience. American equipment reduced operator requirements while providing superior performance. The maintenance analysis proved equally disturbing. The bombsight was designed for modular replacement of major assemblies using standard tools. Gyroscopic assemblies, optical components, and mechanical computer sections could be exchanged in forward airfields by technicians with basic training. German precision equipment required factory-level maintenance and individually fitted components. American technical manuals provided step-by-step procedures with illustrations and troubleshooting guides. German technical documentation typically consisted of theoretical descriptions requiring advanced technical knowledge to apply practically. The documentation philosophy reflected the same democratization of technical knowledge evident in equipment design. Lieutenant Franz Weber discovered that the bombsight included built-in test equipment for verifying calibration and identifying malfunctions. Operators could perform accuracy checks and system diagnostics without external test equipment. German precision instruments required specialized calibration equipment available only at major maintenance facilities. The self-diagnostic capabilities meant that American bomber crews could verify equipment accuracy before each mission and identify problems before they affected operational performance. German crews discovered equipment problems during missions when failures resulted in missed targets and wasted ordnance. These seemingly minor features accumulated into significant operational advantages. American bomber formations operated with confidence in their equipment, reliability, and accuracy. German formations accepted equipment limitations as unavoidable constraints on operational effectiveness. The psychological advantage of reliable equipment enhanced crew performance across all mission phases. November brought intelligence reports that confirmed the team's worst fears about American industrial capacity. Reconnaissance flights over American bomber factories revealed production lines producing B-17s at rates that exceeded Germany's entire aircraft manufacturing capacity. Each bomber required a Norden Bombsight, implying precision manufacturing capacity that dwarfed German capabilities. The reconnaissance photographs showed assembly line production methods applied to precision, optical, and mechanical equipment. American factories produced bomb sights using mass production techniques, while maintaining accuracy tolerances that German facilities achieved only through individual handcrafting. This represented industrialization of precision manufacturing that Germany had never attempted. Dr. Ritter calculated that America was producing Norden bombsights at rates of over 100 units per week. Germany's entire precision optical industry could produce perhaps 10 equivalent devices per month under optimal conditions. The production rate advantage exceeded 10-1 in America's favor, and the gap was widening as American production expanded. The economic analysis revealed even more disturbing implications. American bombsight production consumed precision manufacturing capacity equivalent to Germany's entire optical weapons program. Yet America simultaneously produced submarine periscopes, artillery rangefinders, tank gun sights, and naval optical equipment in quantities that exceeded German production in every category. This suggested industrial capacity for precision components that exceeded German capabilities by factors that defied comprehension. American industry had achieved mass production of precision equipment, while German industry struggled to produce adequate quantities of conventional military equipment. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The strategic implications became undeniable as the analysis progressed. American bombing accuracy would continue improving as crews gained experience with precision equipment. German defensive capabilities would remain static due to industrial limitations. The accuracy gap would widen until American bombers achieved near-perfect targeting precision. Furthermore, precision bombing would enable surgical strikes against specific industrial capabilities. Instead of destroying entire factory complexes, American bombers could disable critical production equipment while leaving buildings intact for post-war reconstruction. This surgical capability would minimize collateral damage while maximizing industrial disruption. The psychological warfare implications were equally significant. Precision bombing demonstrated American technological superiority to German workers, undermining confidence in German defensive capabilities. Accurate targeting of specific buildings showed that nowhere was safe from American reach. The psychological impact multiplied the physical destruction. German industrial workers were already experiencing declining morale due to repeated bombing raids. Precision targeting would intensify this effect by demonstrating that American bombers could strike any target at will. The combination of physical destruction and psychological intimidation would accelerate the collapse of German industrial production. By December 1943, Oberingenieur Wolff completed his final, comprehensive assessment. The classified report concluded that German air defenses faced mathematically impossible odds. American bombing technology provided accuracy advantages that could not be countered through existing German capabilities. Industrial capacity limitations prevented development of adequate countermeasures. The report recommended immediate cessation of strategic bombing defense efforts and reallocation of resources to tactical air defense and fighter production. However, by late 1943, Germany lacked resources to implement fundamental strategic changes. The Norden Bombsight analysis had revealed strategic inevitability disguised as technological assessment. The captured equipment demonstrated that America possessed integrated industrial capabilities that transcended individual technological achievements. Precision manufacturing, electrical systems, mechanical automation, optical instruments, and mathematical computation had been combined into weapons systems that exceeded German capabilities in every measurable category. More importantly, these capabilities were being applied systematically across all military equipment categories. American tanks, artillery, naval vessels, and aircraft incorporated similar levels of automation, precision, and manufacturing sophistication. Germany faced an enemy that had industrialized technological superiority across the entire spectrum of military equipment. The examination team members began drafting individual reports that reflected their growing understanding of American industrial philosophy. Each specialist reached similar conclusions through different technical pathways. America had achieved mass production of precision equipment by embedding technical knowledge directly into manufacturing processes and equipment design. German industry relied on skilled craftsmen who applied technical knowledge through individual expertise. American industry eliminated the need for individual expertise by standardizing procedures and automating precision tasks. The philosophical difference extended beyond manufacturing to encompass training, maintenance, and operational doctrine. Hauptmann Schneider wrote that the Norden Bombsight represented the future of warfare, where mechanical precision replaced human skill and industrial capacity determined military capabilities. Dr. Ritter concluded that mathematical computation had been mechanized to levels that eliminated human calculation requirements. Lieutenant Weber observed that equipment reliability had reached levels that removed operational uncertainty. The individual assessments combined into a comprehensive indictment of German technological assumptions. German doctrine emphasized elite equipment operated by highly trained specialists. American doctrine emphasized reliable equipment that ordinary operators could use effectively. The American approach proved superior under the industrial demands of extended warfare. By January 1944, additional captured American equipment confirmed the bombsight analysis conclusions. Radar systems, radio equipment, navigation instruments, and fire control devices demonstrated similar levels of automation, precision, and manufacturing sophistication. Each device reinforced the evidence of systematic American technological superiority. The accumulated intelligence painted a picture of American industry that German planners had never imagined possible. Precision manufacturing, electrical automation, and mechanical computation were being applied systematically to transform warfare from a craft requiring individual skill into an industrial process, emphasizing standardized procedures and reliable equipment. German engineers realized they were witnessing a technological revolution comparable to the Industrial Revolution of the previous century. Mechanical precision was replacing human judgment, automated systems were eliminating operator requirements, and mass production was making precision equipment universally available rather than limited to elite units. The Norden Bombsight had become a symbol of this transformation. Its brass case contained more than bombing technology. It embodied American industrial philosophy, manufacturing capabilities, and strategic vision. The device represented mathematical certainty applied to warfare, industrial precision applied to destruction, and technological automation applied to victory. The German engineers who examined the captured bombsight understood that they had witnessed the future of warfare. Their detailed technical reports documented not just equipment specifications, but the emergence of industrialized precision warfare. They had analyzed the mechanical embodiment of American victory and found it technically superior, industrially overwhelming, and strategically inevitable. The brass instrument that had arrived in Bavaria in September 1943 carried within its precision mechanisms the mathematical proof of Germany's defeat. The gyroscopes maintained level orientation while German hopes tilted toward inevitable collapse. The mechanical computer calculated bombing solutions while automatically computing the end of German resistance. The optical telescope provided clear vision of targets while revealing the clarity of American industrial supremacy. In the quiet laboratories beneath the Bavarian countryside, German engineers had performed the technical autopsy of their own nation's military capabilities. They had measured the gap between German precision and American mass production, calculated the difference between elite equipment and reliable systems, and documented the transformation of warfare from craft to industry. Their analysis was complete, their conclusions undeniable, and their recommendations irrelevant. The war would be decided not by technological brilliance but by industrial capacity, not by individual expertise but by systematic automation, not by elite performance but by reliable mass production. The Norden Bombsight had taught its lessons with mechanical precision, mathematical certainty, and industrial inevitability. The German engineers had learned those lessons perfectly, completely, and far too late. The spring of 1944 brought a cruel confirmation of every prediction contained in Oberingenieur Wolff's classified reports. American bombers began appearing over German targets with formations so small that Luftwaffe controllers initially dismissed them as reconnaissance flights. Yet these small formations achieved destruction previously requiring massive raids. Precision had replaced mass, surgical strikes had replaced area bombing, and mechanical accuracy had replaced statistical probability. On March 15th, 8 B-17s struck the Messerschmitt factory at Augsburg, with bombs that landed within 10 feet of their intended targets. Critical machinery was destroyed while administrative buildings remained untouched. The psychological impact on workers was devastating. They realized that American bombardiers could place explosives precisely where they chose, that no building offered safety, and that German defensive measures provided only the illusion of protection. Dr. Heinrich Ritter, monitoring these developments from his laboratory, found himself in the unique position of understanding exactly why German defenses had become irrelevant. The mathematical equations he had traced through the Norden Bombsight's mechanical computer were now being applied with deadly precision across the German industrial landscape. Each successful raid validated his calculations and confirmed his worst predictions. By summer 1944, the captured bombsight had been joined by other examples of American precision warfare technology, radar-guided artillery shells that could strike individual buildings, naval rangefinders that calculated firing solutions faster than human operators could track targets, tank gun sights that automatically compensated for range, ammunition type, and target motion. Each device reinforced the same conclusion. America had systematically automated the technical knowledge required for precision warfare. Where German doctrine relied on highly trained specialists, American doctrine relied on mechanical systems that ordinary operators could use effectively. The democratization of precision had become the foundation of American military superiority. Hauptmann Otto Schneider found himself assigned to evaluate captured American tank equipment in July 1944. The Sherman tank's fire control system used gyroscopic stabilization to maintain gun accuracy while moving. German tanks required complete stops to achieve accurate fire. American tanks could engage targets effectively while advancing at full speed. The tactical implications were profound. German tank crews trained for years to master the complex procedures required for accurate gunnery. American tank crews achieved superior accuracy through mechanical systems that eliminated the need for complex procedures. Training time was reduced, while combat effectiveness increased. Schneider wrote in his personal diary that examining American equipment felt like glimpsing weapons from the future. The level of automation and precision suggested that America possessed manufacturing capabilities that would dominate post-war industrial development. Germany was fighting an enemy that had already begun building the technology of the next century. As 1944 progressed, the engineers who had examined the Norden bombsight found themselves scattered across different assignments as German defensive requirements intensified. Wolff was transferred to V-weapon development, desperately attempting to create precision-guided rockets that might counter American bombing accuracy. Ritter was assigned to radar development, trying to create targeting systems that could match American precision. Their efforts were hampered by the same industrial limitations that made American equipment impossible to duplicate. German factories lacked the precision manufacturing capability to produce components to American specifications. Skilled workers were being drafted for military service faster than they could be replaced. Raw materials were increasingly diverted to basic military production rather than advanced technology development. By October 1944, Wolff's team had produced a prototype guided bomb that achieved accuracy comparable to the Norden Bombsight. However, the manufacturing requirements were prohibitive. Each device required 3 months of precision assembly by skilled technicians using materials equivalent to 50 conventional bombs. Germany could produce perhaps 10 guided bombs per month, while America was dropping thousands of precision-guided bombs daily. The mathematical impossibility of competing with American production became undeniable. German industry could not simultaneously produce adequate quantities of conventional weapons and develop precision guidance systems. American industry was producing both conventional and precision weapons in quantities that exceeded German total military production. The final intelligence reports reaching the examination team confirmed the hopelessness of Germany's situation. American bomber production had reached 15 aircraft per day, while Germany struggled to produce 3 per day. American precision equipment production exceeded German precision manufacturing capacity by factors of 20 to 1. The industrial gap had widened beyond any possibility of compensation. Winter 1944 brought the collapse of German air defenses and the end of effective resistance to American strategic bombing. The Norden Bombsight and its associated technologies had achieved their intended purpose. German industrial production declined rapidly as precision strikes disabled critical manufacturing equipment while leaving infrastructure intact for post-war reconstruction. Dr. Ritter spent the final months of the war documenting his analysis of American technological capabilities for post-war industrial planning. He understood that Germany's reconstruction would require adopting American manufacturing methods, precision production techniques, and automation technologies. The lessons learned from the Norden Bombsight would become the foundation of post-war German industrial development. May 8, 1945, Germany surrendered unconditionally, and the engineers who had examined the captured bombsight found themselves in American custody, along with thousands of other technical specialists. They were interrogated extensively about German weapons development, but more importantly, they were exposed to the full scope of American industrial capabilities. Oberingenieur Friedrich Wolff was transported to Wright Field in Ohio for debriefing. The facility housed examples of every major American weapons system, including production models of the Norden Bombsight that had so impressed his examination team. He discovered that his captured example was already obsolete, replaced by improved versions with enhanced accuracy and simplified maintenance requirements. The Americans had continued developing precision bombing technology throughout the war, constantly improving accuracy and reducing manufacturing complexity. The device that had seemed impossibly sophisticated to German engineers in 1943 was considered primitive by American standards in 1945. During his months in American custody, Wolff was given access to technical documentation describing American manufacturing methods. He learned that the precision components that had amazed German engineers were produced using automated machinery that eliminated individual craftsmanship. American factories produced precision equipment through systematic processes rather than individual skill. The revelation was simultaneously humbling and inspiring. German engineering tradition emphasized individual expertise and handcrafted precision. American engineering tradition emphasized systematic processes and automated precision. The American approach had proven superior under the demands of extended warfare, but it also offered possibilities for post-war industrial development. Dr. Heinrich Ritter was assigned to a technical intelligence unit that documented German scientific achievements for American industrial application. Ironically, he found himself explaining German theoretical advances to American engineers who were primarily interested in manufacturing applications. The exchange provided insight into fundamental differences between German and American technical cultures. German research emphasized theoretical understanding and individual innovation. American research emphasized practical application and systematic development. German scientists sought elegant solutions to complex problems. American scientists sought reliable solutions that could be mass-produced. The philosophical differences extended beyond individual preferences to encompass entire industrial systems. By 1946, most of the German engineers were released and returned to a devastated homeland. They found cities in ruins, factories destroyed, and an economy that would require complete reconstruction. However, they also found opportunities to apply the lessons learned from American technology and manufacturing methods. Wolff established a precision instruments company in Munich that specialized in optical equipment using American manufacturing techniques. His factory produced surveying instruments, camera lenses, and scientific equipment using automated machinery and standardized procedures learned during his captivity. The company became one of Germany's first successful post-war technology enterprises. Ritter joined the newly established Max Planck Institute, where he applied mathematical automation techniques to scientific computation. His work on mechanical calculation systems, inspired by the Norden Bombsight's computer, contributed to early computer development in Germany. The mathematical principles he had traced through American bombing equipment became the foundation for civilian computational applications. Hauptmann Schneider found employment with Mercedes-Benz, applying American automation techniques to automotive manufacturing. The precision manufacturing methods he had observed in American weapons production were adapted to civilian vehicle production. German automotive quality improved dramatically as American industrial methods were integrated with German engineering traditions. The economic miracle that transformed Germany in the 1950s was built on foundations laid during the war by engineers who had examined American equipment and learned American manufacturing methods. The precision automation, standardized procedures, and systematic quality control that had made American weapons superior became the basis for German post-war industrial excellence. By 1960, Germany had become a leading industrial nation using manufacturing methods derived from American wartime technology. The Norden Bombsight and other captured equipment had inadvertently provided the technical education that enabled German reconstruction. The engineers who had documented Germany's technological inferiority during the war became the architects of Germany's post-war technological renaissance. Oberingenieur Wolff died in 1973, having witnessed the complete transformation of German industry from wartime devastation to international leadership. His obituary in the German Engineering Society Journal noted his contributions to precision manufacturing and his role in documenting American technological capabilities during World War II. His papers, donated to the German Technical Museum, included over 1,500 pages of technical analysis, documenting American equipment examined between 1943 and 1945. These documents provided historians with detailed insight into the technological factors that determined the war's outcome and influenced post-war industrial development. Perhaps the most significant document in Wolff's collection was a letter written to his son in 1968, reflecting on the lessons learned from examining the Norden Bombsight 25 years earlier. He wrote that the experience had taught him that technological superiority results not from individual brilliance, but from systematic application of engineering knowledge to practical problems. American success, Wolff observed, resulted from their ability to transform complex technical knowledge into simple operational procedures. The Norden Bombsight had mechanized advanced mathematics, making precision bombing accessible to ordinary operators. This democratization of technical capability had proven more powerful than elite expertise available to limited numbers of specialists. He concluded his letter with observations about the nature of technological competition. Nations that successfully industrialize advanced technology will dominate those that rely on traditional craftsmanship methods. Future conflicts will be determined by manufacturing capacity rather than theoretical knowledge. Victory will belong to societies that can systematically apply technical knowledge to practical problems. Dr. Heinrich Ritter lived until 1987, long enough to witness the emergence of computer technology that fulfilled his predictions about automated calculation. His later writings frequently referenced the Norden Bombsight as the first example of mechanical computation applied to practical problem-solving. The device had demonstrated that mathematical knowledge could be embedded in mechanical systems, making advanced calculations accessible to non-specialists. His final academic paper, published in 1985, analyzed the historical significance of automated computation in military affairs. He argued that the Norden Bombsight represented a turning point when warfare began transitioning from human skill to mechanical precision. This transition accelerated throughout the 20th century, ultimately producing computer-controlled weapons systems that exceeded human capabilities in every measurable category. Ritter concluded that the fundamental lesson of the Norden Bombsight remained relevant in the computer age. Technological advantage results from systematically automating human expertise rather than relying on individual skill. Nations that successfully embed knowledge in automated systems will dominate those that depend on human operators. The legacy of the German engineers who examined captured American equipment extends beyond individual careers to encompass fundamental changes in engineering philosophy and industrial organization. Their wartime analysis documented the emergence of automated precision manufacturing that became the foundation of modern industrial technology. Today, the principles they identified in American wartime equipment govern global manufacturing in every industry. Automated precision, standardized procedures, systematic quality control, and embedded technical knowledge are fundamental characteristics of modern technology. The direct line runs from the Norden Bombsight's mechanical computer to contemporary computer-controlled manufacturing systems. The story that began with Oberingenieur Wolff carefully lifting a brass instrument from its protective case in September 1943 concluded with the complete transformation of global industrial technology. The captured bombsight had inadvertently provided a technical education that influenced post-war development far beyond its original military application. The German engineers who documented American technological superiority during World War II had witnessed the future of industrial civilization. Their analysis, written to explain Germany's military defeat, became a blueprint for post-war technological development. They had examined the mechanical embodiment of American industrial philosophy and learned lessons that transformed German industry from wartime devastation to global leadership. In the end, the Norden Bombsight represented more than precision bombing technology. It embodied the systematic application of engineering knowledge to practical problems, the automation of human expertise, and the industrialization of precision manufacturing. These principles, first observed by German engineers in a captured American device, became the foundation of modern technological civilization. The brass instrument that had revealed the mathematical certainty of Germany's defeat also provided the technical knowledge that enabled Germany's post-war reconstruction. The same systematic engineering that had made American weapons superior became the basis for German industrial excellence. The engineers who had documented their nation's technological inferiority during the war became the architects of their nation's technological renaissance. Their story demonstrates that defeat can become education, that analysis can become inspiration, and that understanding the enemy's superiority can become the foundation for one's own success. The German engineers who examined the Norden Bombsight learned lessons that transcended military defeat to encompass industrial transformation, technological development, and economic reconstruction. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.